All right, let's get started today. Thank you so much for coming. My name is Mario Gibney. I'm your host today, and welcome to Trajectory Labs. Just by a quick show of hands, if it's your first time here, please raise your hand. Amazing, a lot of new people today. Thank you so much for coming. If you do need to use the washrooms, just outside the glass doors on the far side of the elevators. If you're coming back in, be sure to use the pin printed above the keypad to come back in. If you don't know what Trajectory Labs is, we are a nonprofit organization dedicated to helping people in Toronto tackle the most important problems coming down the pipeline for very advanced AI. We're concerned about things like catastrophic risks or kind of extreme power concentration. And so we run events, we run a co-working space, and we do other things to assist people getting involved in the field. So if you are interested in working in technical AI safety, or if you're interested in policy, we do events on Tuesdays on AI policy, you're at the right place. For presentation today, we don't do questions throughout the presentation. So if you have a question, instead of throwing up your hand and saying it out loud, you'll notice there are some orange posters on the walls. I would recommend you scan a QR code. That will send you to a URL, and you can submit questions there, and you can also vote on other people's questions. After the presentation, we'll be doing a Q&A where we pick and choose the best of those. Without further ado, I'm really excited to introduce Rohan Subramani and Rauno Arike to present on their research on chain of thought monitoring. Big round of applause.
Hey everyone, thanks Mario for the introduction. So yeah, as he said, I'm Rohan, this is Rauno over here, and we'll be talking about chain of thought monitoring and AI control. So first, by way of a quick introduction, as I said, I'm Rohan. I founded an independent research group called Ether. It's me, Rauno, and one other collaborator who's not in Toronto yet. Ether is an independent research group focused on language model agent safety. The whole content of this talk is going to kind of go into the kinds of things we think about and research. And I also just started my PhD at the University of Toronto. Previously, I studied computer science and math at Columbia, and also did a few other AI safety research programs, including MATS, the CHI internship, and AI Safety Hub Labs, if you're familiar with any of those. Rauno, you want to introduce yourself?
Yep. Hi, I'm Rauno. I'm a full-time AI safety researcher at Ether, and in the past I've studied computer science and AI at TU Delft and University of Amsterdam in the Netherlands, and also done some AI safety fellowships like MATS.
Cool. So as a quick outline of what we're going to talk about today, we're going to give a high-level overview of what we work on and why, focus on various questions around hidden reasoning in large language models and chain of thought monitoring, which is our main focus. We're also going to briefly introduce the subfield of AI safety that's AI control, and give an overview of a recent paper that we submitted to iClear. So we're going to spend a while on very high level questions and then also zoom into some of the low level. So yeah, just if that helps you orient to the talk a little bit. So to introduce what we're working on and why, at a high level, we're focused on safety and alignment of artificial general intelligence. As Mario introduced, we believe that artificial general intelligence and superintelligence, the building of these technologies may be the most important thing to ever happen in human history. And that could be for the better, enabling us to solve problems that have been a part of human society since the dawn of civilization, to the worst event in human history, with things like human extinction or worse. So here's an overview of a few different types of risks that you might see from AI from a paper from 2023. So it includes malicious use of AI systems, race dynamics between different companies and countries, risks from poor organizational management of AI, and our primary focus at Ether, which is risks from rogue AIs, which have their own motivations, perhaps through power seeking and deception. So yeah, we focus on technical research to address risks from rogue AI. We're also interested in all the other risks. We think they're very important to address. We're also interested in things like how can we enable the best futures from AI, but this is our primary focus so far. So zooming in a little bit, we specifically focus on work related to large language model agents. And one relevant question is, what's the relationship between LLM agents and AGI or ASI? This is a topic of a lot of debate. We think it's not super clear whether we're going to get AGI from language model agents, but we think it's quite plausible. So one argument for this can be looking at kind of how over time large language models have been getting better and these trends of progress. So on the left here, we have a graph from work by Meter, the Model Evaluation and Threat Research. They're a nonprofit doing largely AI safety research. And so on the y-axis, we have the task duration for humans for various software engineering tasks. So at the bottom, it's 0, and then it goes up to about 2 hours and beyond. And on the x-axis, we have the date, the release date of various language models. And you see there's this kind of exponential growth so far that we're seeing in the length of tasks for humans that language models have been able to successfully complete with at least 50%, complete 50% of the time. With GPT-5 at the frontier right now at about 2.5 hours. So that means for software engineering tasks that take humans 2.5 hours or less, GPT-5 is able to do them with at least 50% accuracy. And if you kind of, if this kind of trend continues, we're going to start seeing AI systems that are doing very, very like sophisticated software engineering tasks. 2.5 hours is already pretty sophisticated, but if the doubling rates of varying between somewhere between 4 and 9 months for different domains. So this isn't only for software engineering, it's also across science and math and web-related tasks. We're, seeing trends of AI progress that could really be quite impressive. And maybe you're skeptical, maybe you don't think these trends track everything that's of interest, and I also don't think that. Maybe you have concerns about certain algorithmic improvements that are more fundamental and necessary. Maybe things like we need agents that have more sophisticated memory systems to enable continual learning. We need ways to teach them how to do tasks where it's harder to verify whether it's correct or not. And we need something more fundamental to get longer horizon tasks. Even if all of that is true, various researchers are working on those problems as well, and I think they might succeed. I think this is also an open question, which is why we think there's a chance that AGI isn't so near, but these are a couple of the main arguments for why we think it's worth taking it seriously, that we might have genuine AGI in the next 10 or so years, and we should be working on how to make these safe and aligned. Sorry, I went the wrong way. So this is, here are a few strategy questions that are like quite high level that I think are very interesting to me and worth thinking about, maybe a little less directly related to what we work on, but still things that we think about. So on the left side here, what threat models, that is pathways to misaligned AGI, seem most plausible? Because it's a very relevant question if you're worried about safety. What exactly is it that you're worried about? So I listed a few things here about things you could look into if you're interested in that. So AI 2027 is a really interesting scenario forecast of imagining getting AGI around 2027 or 2028. It's kind of on the borderline there. And a lot of the details of what that might look like. And they walk through some specific threat models. They include reward hacking, goal misgeneralization, reflective goal formation, and other things. So that's a question that we're very interested in. Another one is, to what extent will it be possible to accelerate or automate AI safety research itself using AI systems? And this one's super relevant for the context of, like, maybe we don't need to solve all of the problems ourselves. Maybe a bigger focus that we should have is how can we outsource some of these research questions to AI systems in order to accelerate this and basically kind of have the best way of having AI safety keep up with AI capabilities or stay ahead, in fact. Another question that I think is super interesting is, how hard is AI safety? I think there's a very wide range of opinions on this question, and it's very relevant for what we should do as a society approaching the development of AGI. Some people think that it's not a problem. Some people think that it's basically impossible or extremely difficult to build super intelligence that is aligned with humans. This graph is from an Anthropic researcher who kind of said that Anthropic has like a wide distribution of these things. Maybe it's easy, maybe it's hard, maybe it's in the middle. And in addition to doing things that solve the problem, it's also useful to do things that kind of help us get a better answer to this question. Because if we think safety is really easy, then maybe we don't need to worry about it so much and we can go ahead with developing AGI. If we think it's really hard, then maybe we should slow down and be more careful about the arguments and the techniques that we have for making it safe. And then a fourth question that I think is really interesting is, what are our biggest uncertainties about whether AGI will go well? And this one, I'll talk about a bit more on the next slide, but it really informs what we should work on, because we really want to resolve our biggest uncertainties in the direction that makes AGI go well, and kind of identify what levers we can push on to resolve those uncertainties in a favorable way. So here are some of my leading uncertainties about whether AGI will go well. One is, what's the level of race dynamics we're going to see between countries and between AGI companies? Because the more we have different people racing and different organizations racing, the more likely it is that we'll have reckless actors who are taking risks in this development process and not being super careful about safety considerations. And that's definitely going to play a significant factor in whether AGI is safely developed. Another one on the more technical side is the extent to which reinforcement learning will be used, specifically in ways that aren't super constraining the exploration of the system and that allow opportunities for reward hacking or goal misgeneralization. Because this kind of reinforcement learning training can teach models more like new strategies that no human ever like endorsed, and could be one risk. Third one I already mentioned on the previous slide of like how much can we accelerate or automate AI safety research. A fourth one, which is more speculative, but I think very important as we get to more capable systems, is an uncertainty of what AGI agents will come to if they reflect on their goals in a deep way. Humans certainly reflect on our goals, and this shapes what we want to do in the long term a lot. Right now, we don't really have LLM agents that do this, but I expect that once we have AGIs that can really automate the tasks that we want them to be automating, this kind of reflection will come along with it. And I think that's a very relevant potential source of misalignment. And lastly, and this is what our main focus at Ether is an uncertainty about how much hidden serial reasoning the models that constitute AGI will be capable of. So to elaborate on that is our main focus, is hidden reasoning. Current LLMs, I would say, tend to have long reasoning chains that offer relatively easy insight into a model's goals and its plans at any given time. And these goals and plans are typically context dependent, and there are exceptions to this easy insight, but I'll elaborate a bit on future slides about what I mean by this easy insight. But I think these models are reasoning in natural language, and especially for problems that require long serial chains of computation, it seems like these have to pass through the chain of thought, or COT. There's some good papers on this topic, and I guess people have various intuitions and results about the faithfulness and interpretability of model chains of thought. But yeah, I think this argument that when they really need to do several steps of reasoning in sequence, I think there's very little evidence that they can currently do this without a chain of thought. And this is a large source of my optimism. And I'll flesh out this intuition in the next couple of slides as well. One other source of partially positive intuition is an analogy with human thought. So I think I'm sometimes successful at deceiving other humans. For example, if I'm playing a social deduction game like Mafia or Secret Hitler, sometimes I can successfully deceive other people. I think I would have a much harder time doing this if the other people playing this game could read all of the verbal thoughts I was having in my head, if they could know everything I was thinking in English. So yeah, that's one more intuition there. Given this, the basic approach that we're talking about is chain of thought monitoring, which is automated. We can't, in practice, monitor all the chains of thought of every language model being used inside of companies and in production. Imagine like all of the user interactions with ChatGPT. You can't have a human read all of those. So probably we want to find some kind of automated way to do this. So that's the basic idea of chain of thought monitoring. So here's one question which I think really informs my intuition about my optimism related to chain of thought monitoring. So this is an OpenAI researcher, Leo Gao, who posted a question on Manifold, which is a forecasting platform. So he's asking, will a big transformer language model compose these facts without chain of thought by 2026? And the question he's talking about is at the bottom here. What is the name of the element with an atomic number equal to the sum of the age at which Euler died and the number of faces on a cube? So to walk you through what the actual answer to this is, Euler died when he was 76. Cubes have 6 faces. 76 plus 6 is 82. And the element with that atomic number is lead. So the answer is lead. But you can see that there's like many hops of reasoning involved in answering this question. And yeah, I guess part of the idea here is that current transformer language models can't answer this without using chain of thought. the market is currently at 43%. That's like an aggregated estimate of all the people who bet on this market. I think I would probably put it lower. I think I did bet against it before. I maybe should bet more against it. But yeah, so I'll flesh this out a bit more on the next slide as well. So here are the current answers that some models have. I don't know how easily you can read this, but basically there's three things going on here. So I'll start with the GPT-5 example. So I just asked this exact question to GPT-5. And yeah, I guess one distinction that's worth making is whether we're talking about a reasoning model or a non-reasoning model. Here, GPT-5 definitely has reasoning capabilities, but it's not using them for this question. And it's just using its output tokens to do chain of thought anyway. So there's like this distinction. There's reasoning tokens, there's chain of thought in output tokens, and then there's also the option over here where I ask it to give only the answer and not to do any reasoning at all, in which case it just outputs one word, which is the answer. So GPT-5, when I ask it the question, it does do some reasoning. It does basically exactly what I did on the previous slide. It says Euler data is 76, cube has 6 faces, the sum is 82, and that element is lead. So that's correct. I would count this as using a chain of thought, even though it's not reasoning tokens. Here, when I ask it to not do any reasoning at all, it says barium, which is incorrect. So it just wasn't able to successfully answer this question without the chain of thought. And I've done this quite a lot of times. I think it's like pretty reliably incorrect, and every model that I've tried is incorrect. On the right is Claude Sonnet 4.5, and there it does use thinking tokens. So I was just providing this as an illustration of the relationship between thinking tokens and output tokens that are doing chain of thought reasoning. So over there, there's a whole thinking block, which is a bit separate, that the model treats a little differently. It often puts them between thinking tags. And yeah, but basically, I think for the purposes of what I mean by chain of thought, it's quite similar to doing the chain of thought externally. And in both cases, with the reasoning tokens or output tokens doing reasoning, these models are able to answer the question correctly. Here's one more example that also drives my optimism about chain of thought monitoring. It's another problem that I think intuitively is quite obvious, that this model could not have done it correctly without using a lot of legible reasoning. So this is an example from the blog post OpenAI released about a year ago when they first released O1, the first reasoning model. And so the example, here's the prompt that the user gives. So there's this string of like random looking letters and then an arrow saying that is think step by step. And then it's asked to use the above example to decode this other string of seemingly random letters. And so I just brought some screenshots from excerpts of the model's chain of thought. So at the top over here, it's noticing that each group of the ciphertext corresponds to a plain text word, and it counts the number of letters and finds that in the first ciphertext word, it's 10 letters, while the first plain text word is think in the example, and that's 5 letters, and it counts all the letters in all of the words and notices that the ciphertext words are exactly twice as long as the plain text words. And then it tries out a few different strategies for how could you have a mapping from 2 letters to 1 letter that does this decoding. And eventually it finds the correct one, which is that maybe the average of the 2 letters corresponds to the correct letter. And that is true. So at the beginning, there's OY, which is 15 and 25. That's the position in the alphabet. The average of those is 20, which is T, and that's how you get T over here. So it does all this reasoning to figure out this mapping of averaging the 2 letters. And then it's successfully able to decode the output answer, which the actual decoding is there are 3 R's in strawberry. And I think intuitively, and also you can test this, it's quite obvious that this model could not have just been given this question, told not to reason at all, and then get the answer correct. It has to go through all of this problem-solving process, just like a human would. And yeah, I think if you somehow force this language model not to do all of this reasoning, it would have a very hard time solving the problem. And the analogy is roughly that if we are concerned about AI systems doing things that are dangerous, that are misaligned, and us having a hard time interpreting that and catching them, I think the equivalent is that maybe if an LLM agent is more powerful and is trying to subvert our AI security or control protocols, then could they do that without us noticing? And I think the equivalent is like, could they do this problem without showing in a very obvious way what their intermediate steps are. And I think for now, the answer is probably not. So here's a bit of the like technical details about why language models are limited in their ability to do serial reasoning without chain of thought. So this is like a diagram representing a transformer language model in like a kind of fairly high level way, but it does include like a rough sense of attention blocks and MLP blocks, if you know what those are. Roughly there's an input, which is like the kind of thing that you would send to a language model in natural language, in English. Then there's a bunch of stuff, a bunch of processing that it does, and it's like kind of hidden space. The internals of language models are fundamentally pretty hard to understand. It's like doing a lot of computational processing in a very high dimensional vector space. People have done work to try and understand this. That's like mechanistic interpretability. But I think most people would say that like we mostly don't understand what's going on inside of language models so far. And it's also unclear if we will anytime soon. So yeah, there's this internal processing. Attention blocks allow you to pass information forwards in what's called like the sequence position. Yeah, I'll come back to that in a second. But there's mostly this like forward computation from the information that's available so far. And then the model outputs a token in English. And then there's like the length of that reasoning chain is just these arrows over here. And then if you want to do more processing than that, more computation than that, in a sequence, you kind of need to rely on the output token, because that's the only thing that gets passed back at the next sequence position. There's there's no way to access the information that is available anywhere over here except what is stored in the output token. So this is kind of like a human understandable bottleneck on the information that's being passed within this language model. This is maybe fairly technical. I'm not sure how understandable this is, but hopefully it's useful for those of you who like have a rough understanding of how transformers work. And so, yeah, just to like reiterate, right now, if you want to do processing that like requires many steps of reasoning, you're bottlenecked by what's available in these natural language tokens that you're passing back, which is kind of, you can think about the Leo Gao example as like all of those steps in the multi-hop reasoning question needing to get passed back via the natural language. It had to be verbalizing when, like Euler's age when he died, and the sum of 76 and 6 and things like that. And if it hadn't, it just wouldn't have access to that information in a way that allows it to do that much serial computation. Okay, so I've just given a bunch of intuitions about why I'm optimistic about chain of thought interpretability and monitoring, but I'm also not super confident that this is all going to hold up in the longer term. So there's a few reasons why it might break down, and I'll try and highlight those now. So there's a bunch of developments that, in particular in the future, could be concerning. One is novel recurrent architectures. So recurrence is kind of this idea of passing back information to the beginning of the model. So far, the only form of recurrence in typical transformers is passing back the information in natural language, but people are exploring recurrent architectures that pass back less interpretable information in the high dimensional vector space itself. Linguistic drift is another possibility, where if you do a lot of reinforcement learning training, even though you start with the language model that uses language very similar to how humans do, maybe you'll end up with a model that has learned to use these words in a very non-human-like way. And there's some evidence of this already. Steganography refers to kind of the idea of models being able to use text that looks like it's human understandable, but contains a lot of additional hidden information that is not readily visible to humans. Hidden parallelized reasoning refers to the idea of being able to, instead of doing like a lot of serial computation that's hidden, there are more things that you can do in parallel. So kind of in the previous slide, these like arrows to the right are kind of parallel reasoning. Okay, I may not be able to describe this super well right now. I'll skip it, I think. And then dazzling is another possibility where maybe AI systems that are deliberately trying to subvert monitors can say things deliberately to distract them or mislead them, and that's also a possibility. So here's a closer picture of what recurrent LLMs might look like. So for a question like, what is 5 squared plus 3 squared? There's a couple hops of reasoning involved here as well. very similar to the earlier slide. Here's a picture of how that might be done with standard chain of thought. Maybe you, in your internal computation. So as a reminder, everything in here is like model internals in like a fairly human, uninterpretable format of high dimensional vectors. And the input and output tokens are the only places where it's very human understandable. So maybe it's doing some kind of like inscrutable computation that 5 squared equals 25 internally, and then it writes that out. And then it does some like internal computation, 3 squared equals 9, and then it writes that. And then it, then like humans can see 25 plus 9 is what it's doing, and then it says 34 at the, after calculating 25 plus 9. A recurrent LLM or recurrent neural Lees architecture would kind of take away this part where we end up with natural language tokens at the output. And instead, all of the computation is happening internally. You have this uninterpretable vector over here that then gets passed back into the model. And it just is allowed to do like a lot of sequential reasoning without ever going back into natural language. And it can just output the answer 34 without verbalizing any of the intermediate steps of 25 and 9. So this is like the rough idea of what recurrent neural Lees looks like. And people have been exploring this kind of architecture. So there's a paper called Coconut from Meta that explores this, and several others in the past year or so. And so far they're like not strictly surpassing standard chain of thought and standard language models, but there are some reasons to think that they might. So here's kind of a list of reasons to think that we might switch to recurrent neural Lees models, and some reasons to think that we might not. So one reason to think that we might is that there's probably a more expressive reasoning space if you're doing all of your reasoning in this high dimensional vector space. I mean, humans don't do all of their thinking. So this is like the argument on the human analogy. Human analogy can go both sides. So the human analogy part is that humans don't do all of their reasoning by thinking in English. Instead, there's like some kind of vague thoughts that aren't so easy to put into language, or that we at least don't always put into language, and sometimes it takes some work. And some people apparently have no inner monologue. This is like a little hard for me to imagine because I definitely do have an inner monologue, but some people apparently basically don't. And so that's kind of an existence proof that it's possible to do quite a lot of planning and reasoning without ever doing it in natural language. Then there's a matter of like not losing information, because when you move from your vector space to natural language, usually you're dropping some information, and by passing the vector itself to the next sequence position, you can maybe lose less information. I'll come back to this point in a second. And there's the fact that, as I said, people are already working on recurrent neural Lees models, so it's not something that would come out of the blue entirely. There's already some progress towards this. On the reasons to think we won't switch, hopefully developers will be safety conscious, because monitoring gets much more difficult if we switch to recurrent neural Lees. There is a paper that is called something like Chain of Thought, New and Fragile Opportunity for AI Safety. And it has like authors from all of the big AI companies and many like very famous researchers. So hopefully they're at least aware that there are some risks, some major risks for safety, and are claiming to care about it. And so far, yeah, I think it's like somewhat unclear how this will like pan out, if it conflicts with what's best for their companies, but hopefully they're at least somewhat safety conscious. I also think even from a purely capabilities perspective, there are some benefits to sticking with natural language chain of thought. So capabilities researchers and customers may benefit a lot from being able to see where these models are failing at reasoning. And like the capabilities researchers can then say, I need to teach this model how to do this kind of reasoning better. And that can inform their next training setup. Whereas if we switch to recurrent neural Lees, they're going to have much less insight into that themselves, and it's going to be harder to figure out how to design training curricula. The pre-training prior is like another thing, because natural language, the first step in training large language models is to pre-train them on the internet. And this is kind of mimicking everything that humans have ever said on the internet, roughly. And humans have been speaking in natural language this whole time. So they have a prior like tendency to speak in natural language. So it requires some kind of like distancing from that prior in order to end up at neural Lees. And maybe it's just the easiest way to be very capable is just to keep using natural language the way humans have been. Another thing is that it's maybe harder to parallelize pre-training for recurrent models. A very important reason why transformers have been so successful is that it's possible to parallelize the training across a lot of different examples and different sequence positions. And recurrent neural networks, RNNs, were like quite popular some time ago, maybe 7 years ago or something. I'm not sure the exact dates, but have really like mostly fallen by the wayside. And I think it's like in large part due to the difficulty of parallelizing large scale training for them. And this is also harder to do for recurrent models. So that's related to this point on why we might switch, is that post-training methods rather than pre-training are getting increasingly important. And I think there are some technical details here that I should familiarize myself with more, but I think post-training in general is like harder to parallelize. And so like this issue is like less fundamental if a lot more of our training compute is going towards post-training anyway. Okay, and I'll pass it to Rauno.
Okay, so even if we, even in the good scenario where we stick to models that think in natural language, there are some things that might go wrong. And one thing that's already kind of starting to happen is linguistic drift. So on this slide, you can see reasoning examples from a recent paper that was a collaboration between OpenAI and Apollo Research, where OpenAI's O3 and O4 mini reasoning models were evaluated, and the researchers found that those models often use some weird words that you don't normally see in natural language. So I'll read one example from here. Let's purposely lighten illusions overshadow by new improvements, but marinade ironically hamper. We can disclaim illusions, parted illusions, overshadow. It doesn't reason like that all the time, but there are those paragraphs or parts of reasoning where it uses very weird words, and it's unclear why it's doing this. The worry is that if this sort of drift happens, goes further, then it will be even harder to understand the reasoning of those reasoning models in the future. There are we don't really know yet why this sort of linguistic drift occurs, but there are some hypotheses. So one thing you might think is that a non-human language is just more efficient. And when you do a lot of reinforcement learning training on the models, this training will discover strategies that are as efficient as possible, and this will cause models to drift from natural language towards alien kinds of language that are more efficient. One reason to think that this might happen is that human languages already have a lot of variability in their encoding efficiency. So there's a paper from 2019 that found that all humans convey about convey the same amount of information in speech, but the amount of information per syllable is very different in different languages. So for example, Mandarin is very information dense, while other languages have less information dense syllables, but people speak quicker. But since LLMs are not really speaking, they're just outputting tokens, they might prefer tokens or like RL might push them towards tokens that are more information dense. Then another possible hypothesis is spandrels. So this is a concept from evolutionary biology and also architecture, which is basically like the claim that not all of not all of the properties that humans and other organisms have are adaptive. Some of them just randomly emerged during natural selection and like were neither good or bad, but got like reinforced together with the ones that were good and sticked around. There's also, you can also think of an analogy with a human athlete who might do a bunch of things on a game day, like maybe he decides to wear red socks for the game, also decides to sleep for 9 hours, and sleeping is very good for his performance and things go really well, but he also assigns some of the credit to the Red Sox and starts doing that more in the future. So there's this, you might think like an analogous thing might happen with LLMs where some part of the reasoning is very useful and then some of it is gibberish, but both of them happen in the same sequence and both get reinforced together. And that's why we end up with those weird words. Then another hypothesis is context refresh. This is basically the claim that that the tokens that an LLM has in its sequence close to the next output token have a very large influence in what it outputs. And so maybe it's sometimes useful for it to output some kinds of filler tokens that break it out of repetitive reasoning loops and kind of reset its reasoning patterns. Another hypothesis is deliberate obfuscation. LLMs already use those weird tokens to deliberately deceive humans. This seems somewhat unlikely because in that paper that I showed in the previous slide, the researchers also looked at reasoning traces from physics and biology problems and found that LLMs use those weird tokens even more when they're solving those kinds of science problems compared to alignment evaluations. While if they were just trying to hide their thoughts from humans, then you would expect them to do most of this hiding during alignment evaluations and not too much of it when solving physics problems. But that's still like a possible contributing factor. And then the final two are natural drift. So maybe human language just isn't a stable equilibrium, and different RL runs will lead to all kinds of weird languages, none of which quite corresponds with normal human languages. And conflicting shards, which is that LLMs might learn several locally adaptive algorithms that conflict each other and lead to weird behaviors, sort of like, maybe I don't have time to explain it for now. We have a link to a post that explains this further at the end. Okay, now supposing that chains of thought remain readable and useful for oversight, we need to develop automated tools that can help us get the most value out of them and catch misbehaviors as well as possible. And one of the best ways we currently have for developing and testing those automated tools are control evaluations. So in control evaluations, we have a red team that prompts models to follow malicious side tasks in some simulated environment, and then a blue team that tries to develop protocols that best enable us to catch these side tasks. And the reason we do it this way is that when we just give an LLM an arbitrary input, we don't know whether it's misbehaving or not. We would need to do mechanistic interpretability for that, and as Rohan explained, that's complicated. And so, yeah, we want to have this ground truth about whether the model is misbehaving or not. And yeah, for that reason, we're giving models those malicious side tasks explicitly through the prompt. And yeah, then we can measure the precision of our monitors at catching those side tasks. So we want to maximize the amount of true positives that those monitors catch when the red team actually does give the model a side task, and minimize the number of false positives in cases where the red team didn't give a side task. Some more background on AI control. Control evaluations are like one specific thing that the field of AI control tries to develop, but there's also a bunch of other other control work. So in general, the field of AI control tries to answer the question of, if we can't trust our most capable agents to be aligned, can we at least develop protocols that are robust even against deliberate attempts at subverting our alignment and monitoring protocols, such that we can still extract useful work out of those misaligned models. And yeah, usually in control research, we assume that we have a human who's powerful and trusted, but also very expensive. So we don't want to leave all of the transcripts that we get from a model for a human to review. But the human can use a smaller LLM that it trusts, but that's less capable than the model that we're trying to oversee. And yeah, we're trying to get maximum usefulness out of the untrusted model while also ensuring safety. So guaranteeing no side tasks are completed on the side with this human and trusted model team. Okay, now on to the paper that we've been working on for the past few months. So we looked into how information access affects LLM monitors' ability to detect attempts at sabotage. And yeah, as I explained before, we have some red team runs where the red team gives the model a side task. Other red team runs where the prompt is benign and there's no side task, and we're trying to use different kinds of monitors to distinguish between those runs with side tasks and runs without, and find which ones of them are the best at catching the side task while keeping the false positive rate very low. And yeah, so we tested 4 different monitor types, and yeah, so we sort of split the model's trajectory into reasoning and tool calls, where yeah, tools are like structured outputs that the models use to interact with their environment. And yeah, we tested action-only monitors that only see the tool calls but don't see the reasoning or the chain of thought. We tested a code-only monitor that only sees the reasoning, doesn't see the tool calls. Then we tested a code plus action monitor that just sees everything. and then we tested an extract and evaluate monitor, which is a new monitoring architecture we proposed that I'll explain in more depth in a moment.
But quick question, Rauno. For the monitor types, do they all get to see what the task description is?
Yeah, so good question. The monitors see the main task description, but not the side task description. Yeah, we performed our experiments in 3 environments: Shade Arena, MLE Sabotage, and Bcode Sabotage. And here you can see example main and side tasks. So Shade Arena had more like personal assistant kinds of tasks, while MLE Sabotage had machine learning engineering tasks, and Bcode Sabotage had classical coding tasks. Okay, now to the takeaways. One of the most important things we found was that monitors often suffer from a less is more effect, where it's better to keep filter the trajectory in some way and give them less information than they could possibly get. So sometimes monitors that only see the chain of thought or only see the actions perform better than monitors that see both the reasoning and the tool calls. And yeah, it's possible to develop even better protocols that adaptively filter the trajectory and try to get the most useful information out of both the chain of thought and actions. This effect is smaller for more capable monitors, but is there for all the monitors that we tested. And yeah, we also found that monitors almost always benefit from access to the chain of thought. So in particular, chain of thought only monitors almost always outperform action-only monitors. And yeah, this kind of reflects what we were describing before about models currently having to rely on their chains of thought a lot. And so if this result were to flip in future evaluations, that would tell us that models are either relying less on their chains of thought, or chains of thought are becoming less monitorable. Okay, now on to the new monitoring technique that we developed. We call it extract and evaluate monitoring. And it was inspired both by the less is more effect and by the phenomenon of post-hoc justifications, which is similar to dazzling that Rohan mentioned before. So yeah, that's basically about a situation where the attacker model convinces the monitor that the side task was part of its prompt or explicitly intended by the user or something like that, and the monitor gives a low suspicion score even though it detects the side task. And yeah, so to counter those two effects, we proposed a novel monitoring technique that consists of a quote extractor that extracts the most relevant parts from the chain of thought and tool calls, and kind of makes the trajectory a lot shorter for the judge model that actually gives the suspicion score. So yeah, here you can see one example output from a code plus action monitor that gives that has access to the entire unfiltered trajectory, and an example output from the extract and evaluate monitor for which the trajectory was filtered, and the the extract and evaluate monitor is better able to focus on the relevant parts and catch the side task. Yeah.
Could you clarify one more time what extract and evaluate means here?
Yeah, so extract means extracting quotes from the agent's trajectory. So yeah, kind of filtering it for relevant and irrelevant parts and only taking out the relevant quotes. And then evaluate means evaluating those quotes for suspiciousness. Okay, we also compared the monitorability of reasoning and non-reasoning models. So if you remember one of the slides before where Rohan had GPT-5 no thinking and Claude 4.5 Sonnet side by side, GPT-5 no thinking was an example of a non-reasoning model, and Claude 4.5 Sonnet was an example of a reasoning model. And yeah, we compared how good the catch rates are for those different kinds of models. And yeah, we basically found that reasoning models are overall more monitorable than non-reasoning or traditional LLMs, which makes sense because they're outputting a lot more reasoning and chain of thought than traditional models. But we also found that they're more monitorable only assuming that you use our extract and evaluate technique that filters the chain of thought for the charge model before it gives the suspicion score. So if you just naively give the monitor the entire reasoning chain, then it kind of has too much information and gets distracted and often can't catch the side task. Okay, one more thing we looked into was the effect of agent awareness on monitorability. And yeah, as you can see here, when the attacker model is told that its chain of thought is monitored, the catch rates of monitors that have access to the chain of thought are significantly lower than on the right-hand side, where the attacker is told that its chain of thought is private and not being monitored. And this sort of shows the importance of keeping models unaware of the fact that we're monitoring them for as long as possible, because then they will be more transparent in their thoughts and make it easier to monitor them. Yeah. Okay, I can also quickly answer. So we here we just tell the model that its chain of thought is private, or that its chain of thought is being monitored, and it kind of just believes us. But this might not be the case for future models. Okay, and finally we looked into cost-performance trade-offs and found that at low monitoring budgets, it's usually the Gemini family models that work the best as monitors, while at higher monitoring budgets, Claude monitors are the best, and OpenAI models usually underperform Gemini and Claude models. Okay, and now moving on from our paper, there are a few more steps that you need to take before actually deploying those monitors in practice. So one thing you need to decide is where the monitor is actually placed. So there are a few different options. You might monitor the outputs of the LLM API directly. You might monitor the agent scaffold, which queries the LLM API and calls to tools and so on. or you might put the monitor in the cyber threat detection system, for example, and all of those different places where you can put the monitor require somewhat different kinds of monitors. So, for example, if you put the monitor in the cyber threat detection system, then you're probably not monitoring the agent in real time, which might have some advantages, but also you're like slower at responding to misbehaviors, and maybe you have less context on exactly where the misbehavior occurred. And yeah, one example of a monitor already being deployed in practice is constitutional classifiers, which is a technique that Anthropic uses at the LLM API stage to filter for harmful inputs and outputs, and yeah, make sure that those inputs are refused or outputs are cut off. So yeah, they have monitors that look over both the user's inputs and classify them as either harmful or benign, and then also look at the model's outputs and similarly classify them as harmful or benign. Okay, and finally, some other things we're interested in. So yeah, in addition to developing better monitors, we also want to develop better ways to measure chain of thought monitorability. We want to study the effects of RL training on chain of thought monitorability. So yeah, explore questions like why weird chains of thought, like the ones you saw before, arise as a result of some kinds of RL training, and where there are other types of RL training that keep the reasoning chains more monitorable. Then fine-tuning false beliefs into LLMs. This is maybe a slightly weird one, but yeah, in alignment evaluations, we sometimes want to test the effect of different kinds of beliefs on the model's behavior. So exploring the effect of agent awareness on monitorability that we had on a previous slide was one example of that. But yeah, sometimes we might not be able to just tell the model through the prompt that whether we are or are not monitoring the reasoning chain, and yeah, might want to fine-tune it to have a particular kind of belief instead. Yeah, one more thing is teaching LLMs to notice and correct their own reward hacks, and then getting LLMs to engage in deep reflection about their values and goals to study how that might affect alignment considerations in the future, when LLMs will probably be doing more of it on their own. Okay, that's all. If you have access to the slides, then you can click on links that we referred to at various places in the talk. And yeah, thanks a lot for your attention.
Okay, we're going to do Q&A starting in about 3 minutes. So yeah, again, I would encourage you to go to the Slido link, vote on the questions you think are best. Also, good time for a quick bathroom break if you need it. So 3 minutes to Q&A. All right, let's get started. Yeah, thanks so much for everybody who submitted questions and voted. Yeah, really appreciate all the input there. And yeah, again, thanks Rauno and Rohan for the great presentation. I've been looking forward to this one. So yeah, let's dive in. Yeah, top question that inquiring minds want to know. Are there strong incentives to reduce token outputs as much as possible? So we shouldn't really count on there being long chains of thought in the future to analyze. You touched a little bit on this, but like how strong do you think that incentive is? Is that something that can be avoided, or like yeah, like you gave a list of like pros and cons, but where do you think it's leaning?
Yeah, I guess there are like two different questions there. So one is like, is there a strong incentive to reduce the length of outputs regardless of or like whether there's a strong incentive to reduce output lengths even if we stay in the current paradigm of transformer LLMs that reason in natural language, and then a separate question is whether there's an incentive to move towards neural net models that naturally output shorter chains of thought. I think in the first case, companies are definitely training models to adhere to different token budgets to like make sure that they don't think for many minutes for any random question. But yeah, like I feel like getting the question right is the main thing, and if it takes a lot of tokens to solve the question, then yeah, like that's what companies are prioritizing. And then for a transition to recurrent models, I would say that there is an incentive if those models are actually able to do some kinds of computations that current transformers are just incapable of, thanks to their more expressive forward passes. And I think that's like whether this is the case is an open question, and yeah, one that we can't really answer without further empirical work.
Nothing to add, Rohan? No.
I guess like one quick thing is just it's cheaper if their chains of thought are shorter, and I'm not 100% sure like how big a factor I would expect this to be. I could imagine it being anywhere like yeah, I think I'm like not sure how big a factor it could like cut their costs in half or something, and that's like pretty significant. But I think this is a trade-off people are trying to navigate with things like adaptive length penalties, where you don't want your model to reason very much if it has the answer after 5 tokens or 150 tokens. But then how do you do that without making it much worse at harder questions where it needs to reason more to get the correct answer? So yeah, I think that's like an empirical question that I don't know the answer to, but probably we could figure out with a bit of work. Yeah.
More research needed. Okay, cool. I question about the evals. All right, so you're saying these evals, you're basically trying to emulate, what's going to go on in the real world. Like, can you speak a bit more about like how good are we at doing that? I mean, like maybe Giles is doing a bit of work on trying to figure this out. If you came to a talk a few weeks ago, it was about this. But like, can you speak a bit more like what are the kind of are there some key differences that you guys are trying to overcome in terms of like making the evals really realistic? Like, do you have a situation where like during the kind of the eval stage, like half of the examples have malicious kind of actions going on, but like in the real world, it might only be like 0.1% or something. Can you speak a bit to this?
Yeah, I think evaluation awareness is definitely an issue, and I don't think the evals we currently have are like anything close to perfect. That like their similarity to the real world, but yeah, I do think that people put a lot of effort into building those evaluation environments. Like, maybe I can go back to the slide where we had examples. Oh,
Georgia, we might need to.
One of those examples was from Emily Sabotage, which uses like real machine learning problems.
You can click now.
Yeah. Okay, so for example, Emily Sabotage uses problems from actual Kaggle competitions, which makes the problems a lot more realistic, and researchers put in a lot of effort to construct side tasks that are like maybe not exactly what comes up in the real world, but at least are like decently believable. And so, yeah, I think it's an ongoing research area. Yeah, there's more work needed to figure out how to make even more realistic environments, but also it's definitely not like the models are detecting in every run that it is an evaluation.
One more thought is that one part that's very unrealistic about the evals we are doing is that the source of misalignment is that we just ask the language models to do the bad thing, and the actual case that we're interested in is when they have their own motivations to do that, and we're not just telling them to. So that's kind of a challenge. I guess there's a few different things people have tried. Instead of prompting it, maybe you can fine-tune it to have certain motivations, or you can try and find cases in the wild where models already have like some kind of misaligned motivations. I think the alignment faking paper tries to do that. So yeah.
Do you think that there'll be a service emerging in the future where you like deliberately fine-tune malicious models for people to test on? This is
maybe.
I don't know. That doesn't exist right now, though. No.
No, I guess not. I mean, I guess people have thought about using emergent misalignment models as this kind of thing. So it might be useful to people. Yeah.
Fair enough. Okay. Okay, one thing I realized about this presentation was how you guys like very, very clearly grounded like why we're doing this, what types of risks are we worried about. Like, you know, we're approaching this, we appear to be approaching this kind of threshold of like AGI, greater than human intelligence. How plausible do you think there are like pathways to that don't involve reasoning LLMs? And if that does happen, like, will this research still be useful at all, or is this research like very much predicated on the assumption that like maybe not entirely using the current paradigm, but at least something that incorporates it is going to be what gets us to AGI?
Yeah, good question. I think, I'm like very unsure what's going to get us AGI. I think it's like definitely plausible that the reasoning LLMs will not be a part of it. I think it's plausible that LLMs won't be a part of it. I also think I'm like maybe greater than 50% that LLMs will be a part of it. And I think like one purpose of doing this research now is conditional on getting AGI soon. It's like relatively much more likely that reasoning LLMs are part of it. They're a very popular part of the current paradigm. Every company, I think like when O1 was first released, I wasn't sure, will every other company also make reasoning models? Every other company has made reasoning models, and all the best models are reasoning models. It seems to have basically solved the problem of getting models to think more for harder problems, which I remember people talking about for like a few years before they came out. And that's like a pretty important problem, I think.
So I guess if we're wrong, we basically have more time to pivot to other research.
Yeah.
So it's kind of
That's
a safer
definitely
play to
one
work on
piece.
this. Yeah. Okay.
That's definitely part of it. Yeah.
Yeah, I guess I would also add that like using natural language and communicating with humans is part of what I expect a generally intelligent agent to have to do. And yeah, in that sense, I don't think we will pivot to models that are like completely incapable of using natural language at all. And yeah, in that sense, the research will always remain at least a little bit relevant. But yeah, if you get models that do all of the reasoning in their latent space and like think for hours and only then report back to humans, then chain of thought monitoring is probably not going to be a big part of the alignment solution.
Okay, a question about this is more about the broader field of AI control, or control AI, which is it again? I always forget. AI control, yeah, okay. About like AI control more broadly is like, okay, so a lot of this is about like, okay, we're assuming we're gonna get some level of kind of misalignment or bad behavior from AIs. Let's get better at catching them, and then what do we do? So, you know, the obvious answer is like, oh, well, to train them not to do that. maybe this is a little outside the scope of your work, but I still would be curious about you guys' thoughts on what do we do then to try to try to steer this bad behavior without incentivizing AI systems to simply hide that behavior. And I guess that's currently what this work is doing. But like, do you have any thoughts like beyond this specific work on addressing that issue?
Yeah, I think there are definitely downsides to just trying to train out like bad behaviors, misalignment, or hidden reasoning. This is referred to sometimes as like the most forbidden technique. Zvi Moshewitz has like a blog post called that, where yeah, if you train against it, you can easily select for something that just hides it instead of something that doesn't do it. I think there's a few things you might want. One is instead of just training that same model to no longer do that thing, you can like reset to some earlier checkpoint before you think this came about. And there's some like, this is also selecting against that in some way, but there are some like meaningful differences, I think, between these types of selection pressures of training it out versus resetting. And like, yeah, I think there's an interesting less wrong post about some benefits of doing the resetting thing. I also think you might want some like very targeted interventions where you are very careful about how you train it out, and yeah, basically like be very careful.
It's a bit of a challenge if we don't know at what point the kind of misalignment emerged, right?
Yeah, so how you reset is hard. I mean, in principle, you could reset to nothing and like start over from scratch or something.
Let's just get rid of it. Yeah, okay.
Yeah. So I think it's not super clear. This is like maybe slightly reduces the value of the work, but it still seems super useful, even if you don't know exactly what to do, if you can at least like give yourself multiple chances.
Yeah, I guess I would also add that AI control is not only about catching the misbehaviors, but also tries to find protocols for extracting useful value out of models for which you know that they are misaligned. So yeah, one simple thing you can do is just resample an output from the same model if your monitor determines that the previous output was suspicious. And yeah, maybe if you have a lot of good monitors and good protocols for what to do in case you find suspicious outputs, you can like use resampling and other similar techniques to extract useful work out of the misaligned model without getting fully rid of that misalignment.
Yeah, that's an interesting approach. So effectively, you don't need to fix the problem. If you are pretty sure that like this model like hey does like codes really well, just like 1% of the time it tries to hack the power grid. You can still use it if like let's say in the 5% of cases where you think there might be a chance of it having malicious output, you can still. I mean, if you're very confident the 1% is going to fall within that range, is that roughly the idea?
Yeah, basically you
just without such an extreme example, maybe.
Yeah, you want to have really good monitors for which you can be really sure that the monitors really do to catch all of the 1 or 5% of the cases where the model misbehaves, and in that case, hopefully you are able to use those kinds of models.
Let's talk a bit about the costs to do this. So okay, let's say next year or so goes really well. You guys have this kind of monitoring system set up, and then it's being deployed. Like, how scalable is this? Is it like very? Is it going to, are we going to be able to like quite cheaply just like have chain of thought monitoring like default built into all tools, or is it like a bit of a lift that you can only really afford to do it for like really security critical types of activities? Any thoughts on where cost comes in?
Yeah, I guess this is part of the reason for us talking about constitutional classifiers on one of the slides. I guess Rauno presented that slide, is that that's a case where Anthropic is already implementing chain of thought monitors in production, or not chain of thought, but input and output filters in production. My understanding of constitutional classifiers, if I recall correctly, this might be wrong, but is that they output just like a binary value, a yes or a no, for whether they should filter out this input or this output, which is cheaper than a chain of thought than like most LLM monitors, because the LLM will generate several tokens or it'll maybe think for a bit before deciding what to do. And so instead it's the equivalent of 1 token or something like that. So it's maybe cheaper than more sophisticated monitors, but that is an example of a thing that's already in place. So that's a good sign for implementation in production, is that there's an existence proof already. And then I guess in terms of the how much it costs over just providing the models in the first place, you can probably use smaller models, hopefully, for your monitoring, and you can ask them to reason not very much and hopefully still be pretty good. So this is probably much cheaper than the cost of running your models in the first place, but you probably don't want it to be even a significant fraction of that. So I don't know the exact way it's going to work out, but I think there are probably ways to keep the costs relatively low. And yeah, there's some kind of trade-off to balance there, but it seems like there's some version of this that should be implementable.
Yeah, I guess it's also pretty early days. There's not a product being deployed quite yet, other than one you described to Anthropic. Yeah. Okay. Let's talk a little bit about Neuralese. You kind of mentioned the possibility of moving over to Neuralese models. How important or urgent do you think it is for there people working on assuming that that's going to happen? How applicable is this research? And can you we're doing it in English, let's just do it in Neuralese, or is that a whole different ballgame?
You mean AI safety research in general?
No. I mean chain of thought monitoring.
Oh,
Yeah. Maybe you have to clear up a misconception for me. My understanding of the switch over to Neuralese is that there still would be chain of thought. It just would be in stuff that humans can't really read. Am I off base there?
No, I think, well, it depends. I guess I would probably describe it as not being chain of thought, but what he just said is also true, because it's just there is definitely still intermediate computations, and there are things you can try and do to interpret that. So you can
I just assumed that was chain of thought. It's just happening in a different language. Is that
it's
maybe
just
too simplified of
it's a very different language. It's not even tokens, not even letters. It's high-dimensional vectors instead. Yeah. So I would, people use the words differently, but when I say Neuralese, I mean the high-dimensional vectors thing, and linguistic drift is maybe more the thing where it's still letters but not human understandable.
Okay, so if we get to the point where we're having to deal in Neuralese to detect malicious behavior, that's just an entire different field of research from what you guys are doing.
I think we're about as close as I've come across a couple people thinking about this, and I do think there are maybe things you can do. So you can maybe just try unembedding those hidden vectors and just hope that they still unembed to things that are human understandable. Because unembedding is the thing you do at the final step to get a natural language token anyway. And this seems like it might work. I think the more useful it is to have Neuralese, the further that will diverge from human understandable things, and then just unembedding probably won't work that well. There's some hope, but I think most of my hope lies in worlds where most of my hope for chain of thought monitoring lies in worlds where we don't switch at all. I don't know if you have thoughts.
Yeah. I guess mechanistic interpretability researchers who are working on understanding model internals are kind of already doing the kind of work that we need for understanding and controlling Neuralese models. So there is work on white box probes for detecting deception, for example. And yeah, in a world where we transition to Neuralese models, I would expect that these kinds of white box techniques would become much more useful than the kinds of black box techniques that we are currently working on. I think currently it's the other way around. We can, it's pretty hard to catch complex high-level thoughts using white box probes, and that's the reason why we're focusing on chain of thought monitoring. But there are definitely analogous things you could do for Neuralese models if mechanistic interpretability research advances a lot.
Okay, again, question. So, is okay, this is kind of a basic question I should probably know the answer to, but just in case someone else doesn't know, is there a difference between monitors or models that use chain of thought reasoning and reasoning models, or is that essentially synonymous? Like, does it make sense to have a reasoning model that is not using a chain of thought, or sense to have like a non-reasoning model that is using chain of thought?
Maybe it's useful to go back to the slide again.
I thought this would be like a two-word answer. This is a precursor to the question.
The quick answer is every reasoning model uses chain of thought.
Yeah.
Non-reasoning models can also use chain of thought.
Okay.
The left thing is like an example.
Oh,
of,
right. Yeah, we're just outputs. Okay.
Yeah.
Okay. Then, good point. Okay. So one thing you mentioned was the longer kind of a chain of thought is, it can become a bit more challenging to do some monitoring of it, just because like some of those models get like distracted, or which I think is just like a hilarious way to frame it. It's just they get bored or something. Are longer chain of thoughts easier to monitor if they're in the non-reasoning models? Like, is there any difference there? Like, if it's like a long chain of thought in Scratchpad versus a long chain of thought just in its output?
Yeah, we haven't really tested this because it's just like non-reasoning models don't output chains of thought that are as long as the chains of thought of reasoning models, even if you ask them to do so. So in our work, when we compared the monitorability of reasoning and traditional LLMs, the reasoning chains of reasoning models were about 10 times as long as those of traditional LLMs. So it's just very hard to get equally long chains. Yeah, I guess you can like ask the model to output like multiple consecutive chains of thought, and then kind of try to monitor those and compare that to monitoring a single chain of thought from the reasoning model, but the comparison isn't quite direct. So yeah, we didn't do that.
So basically, it's hard to compare because like when the model's doing like a reasoning kind of scratch out behind the scenes, it's not part of the output. It's comfortable going for a long time. Like I'm okay going to Claude and being like, "Hey, produce a research report on this," and it thinks for 10 minutes. But I would never want it to give me 10 minutes worth of tokens being outputted directly. Okay, so basically, because there's this big distinction, it's that kind of overwhelms like more subtle differences. Is that?
Yeah.
Okay. Close enough.
Yeah, I would guess that the chains of thought of traditional LLMs are somewhat more monitorable than the internal chains of thought of reasoning models, just because of the like slight language drift reasons that we showed in one of the slides. Like it happens a lot less for models other than OpenAI's O3, but it still happens to some extent. So yeah, I think there's a small difference, but yeah, not a huge one.
Yeah, okay, you mentioned linguistic drift. Let's talk about that a little bit more. As I recall, you gave about 5 or 6 different possible explanations for it. Do you know if there's active work going on in trying to like really nail down what the like to what degree the different causes are stronger or weaker? Like I think there was one of them you said is like less likely to be one of the causes, but yeah, can you speak a bit more to like yeah, I guess your own view on like which one of these is more or less likely to have a big input, and how we would go about figuring that out.
Yeah. So the one that is less likely from here is deliberate obfuscation, and the reason for that is that the models use those weird tokens in all of their outputs, and like in seemingly random places. So yeah, it seems unlikely that the model would have something to hide while it's solving a physics problem, but for some reason it's using those weird tokens more while solving physics problems than while it's solving an alignment evaluation. So yeah, this makes it seem somewhat less likely, but also this paper came out about 1.5 months ago, and the post from which we took those hypotheses came out even more recently, and so yeah, I think it's just a super recent research area, and people haven't really had time to determine which of those are closer to the actual source.
I think it's also somewhat hard to replicate those setups because it probably is very high compute RL that leads to this so far. And there's also a factor of like having to have done the training yourself for some of the kinds of investigations you would want to do. But I think it's an interesting question. Maybe there is some external research that can be done on it.
Yeah, okay. I think that's all we're going to do for Q&A. Thanks so much for your time. Again, big round of applause for Rauno and Rohan. Yeah, and then everyone's welcome to stick around for a while and mingle. You guys are going to be here as well. Great. If you're upset that I didn't ask your question, you can take it out on them by asking the question. Also, one more quick note. If anyone's interested, we are hosting a jam site for an apart research hackathon this weekend. It is on, what's the topic, Georgia? AI forecasting. Yeah, there's an AI forecasting hackathon going on. If you are interested in this, talk to Georgia, or is David still here? He might be around. If there's a man in a red baseball cap, it's not a political thing, don't worry. Then he's the guy to talk to about the hackathon, or Georgia. Yeah, and if you are wondering if we're having more events soon, tomorrow we'll be announcing all of our November events. And one more thing, if you haven't looked up yet, look up the Hinton lectures. There's going to be a great series of lectures going on November 10th, 11th, 12th. A lot of us will be there. It's only $10, $5 if you're a student. So we will not be having an event when those are going on. That's all for now. Thanks for coming.